No more measurements, no, lots more measurements.
Had too much from yesterday for it to be a shop class, bro.
Well, we're not gonna be measuring like with a ruler. You did miss a little bit of notes yesterday, Cash, on that
Did
page.
I?
Yes,
This one?
yes. So, gonna want to get those filled in, but it's only part of it.
My IP says you're supposed to give me all my notes.
Hmm?
My IP, I'm supposed to get all my notes given to me. I have my transcript up right now, so you can see.
Take a look at it in a bit. Okay, can we put laptops away? I see a couple of them. Gosh, not right this second. Okay. So, today you might want a calculator. If you don't have one, grab one, please.
Here's the program, bro.
Okay, so yesterday we talked about, our main focus was focusing in on congruent segments. For segments to be congruent means they have the same measurement. Now we are not in this class going to be pulling out a ruler to start measuring lines. That's not the point. When we talk about measurements in here, we're often dealing with just kind of diagrams that represent a certain length, not that you could take a ruler and measure them. So, if congruent means having the same measure, and we can see congruent in pictures by tick marks, one of the things that allows us to do is it allows us to solve for things. I've got this picture right here. Do you see a bunch of tick marks on it? The single tick marks are hanging out here and here, meaning those two things are congruent. Those things have the same measure. They are the same length. What is a math symbol thing that means same? Equal sign. So that means this 3x minus 7 is equal to negative 5x. Now the question asks us to solve for the variables. In other words, solve for variables are the letters. Figure out what x is equal to. I want to get x alone. When I have 3x minus 7 equal to negative 5x, how do I solve? Add 7. Now that is an option. Can I add it to the negative 5x? No. If I were to add 7 to both sides, it would just move over here. But there's not a plain number over here. So while you're not wrong, we can add 7. There's a faster way to do this. And that's minus the 3x, because the right side currently only has a number x, which means it's easier to move the x's that way. It'll be faster. So I'm going to do it that way, if you don't mind. Those will cancel out. What's it leave me with over here? Negative 7. Be careful with that. Equals. What's negative 5x minus 3x? Negative 8x. How do I get x by itself? Ooh, which one am I dividing by?
Oh, negative 8.
Negative 8. Because that's what's in front of the x. It is very common that people accidentally divide by the other one, so just be careful with that. So I got negative 7 divided by negative 8. That is not the prettiest decimal in the world. Is it terrible when it's only 3 decimals? No. Does a decimal mean something's wrong? No. You can have decimals. And if it's just 3 decimals long, I'm just going to write the entire thing. Sometimes it'll say round to the nearest hundredth. Do y'all know how many decimal places are to the nearest hundredth? 2. Little trick for ya, if you don't know this already. If I ask you to round to the nearest hundredth, think about the base word. Base word of hundredth is 100. How many zeros are on 100?
2.
That's how many decimal places it is. That's one kind of trick you can use if you're ever stuck with how many decimal places. Number of zeros is the number of decimals. So if I said round to the nearest millionth, I'm never going to say that, but if I said that, how many zeros are on a million? 6. So how many decimal places would you be going? It's kind of a quick memory trick. Now this one didn't say anything about rounding, so I'm just writing the entire thing. Is that the only variable in the picture? Or do you see other letters? There's lots of letters. Now, is the capital letter right here a variable? It's a point. Generally speaking, lowercase letters are what we use for variables more often. That's part of the reason why geometry got so picky about doing capital letters for points and lines and planes most of the time. Okay, so other variables that I see x's. We did that. There's y's and there's z's. So, do you want to solve for y's next or z's next? Sure. I see the z right here. Do you notice it's on the triple segment mark? Which one is it congruent to? The one that's marked as 16. So, 2z minus 5, that's the entire segment, is equal to 16. I want to solve that. Where am I starting? Plus 5. 16 plus 5 is what? 2z is equal to 21. Divide by 2. Z is 10.5. Okay, still need to solve for the y's. I see the y right here. It's on the double tick mark. Where's the other double tick mark? 14, which means 4y is equal to 14. This one's much simpler to solve. Divide by 4. 3.5? Did I do that right in my head?
Yeah.
Sweet. So that's solving with congruencies. You find what it's congruent to, you set it equal, you solve. You think we can manage that? Okay. There's another thing we're talking about today on the next page. It's definitely not bad. So, one of the things that we have to talk about in geometry is some of the pickiness of certain things. The things like lines have to be straight and have to go on forever is one of the pickinesses of geometry. Another pickiness of geometry is how you call things being between one another. In geometry, okay, if I stand right here directly in front of, that's Mr. Carter in the back, if you don't know that, by the way. He's another teacher. If I stand here, would you say that all of you are sitting somewhere between me and Mr. Karna?
No.
Would you say many of you are?
Some.
Okay. Is Jace sitting between me and Mr. Karna? Some people would argue yes, some people would argue no. Because in the span of the room, for me to get from where I am to him, do I have to walk by Jace? In some shape or form? In the most direct route? Yeah. And so in real world, oftentimes we do that. We say things are between. Now let's make it a little more complicated. I'll stand over here. Are all of you somewhere between me and Mr. Karna?
Yeah.
Somewhat yes, somewhat no. Some of you that are on the outer spaces, maybe not. But if you're kind of in the middle-ish, are you? Kind of. In geometry, they're picky. In geometry, the word between means exactly on the same line to be between. Because if I looked at this picture, E kind of looks like it's between D and F, but it's not perfectly. So this is considered not between. Well, in this situation, my goodness, I can't write. We do have a between situation. B is between A and C. While in this one, I should have written the full sentence first. E is not between D and F. In other words, using our actual geometry terms, 3 points have to be collinear for us to say any of them are between the others. They have to be on the same line. Now, why is that important? Well, comes down and gives us this postulate. Now, I've mentioned postulates in here before. A postulate is something that can be proven to be true, that's something that is true, but you don't need to prove that it's true. It's called the segment addition postulate. Segment addition postulate starts off with kind of looking like a picture that looks like this. A segment with an additional point between. And on this segment, I'm going to call the points A, B, and C, where A and C are the end points. Now, the segment addition postulate, in many ways, you probably know kind of how it works already. Because if I was to skip talking about the segment addition postulate, if I were to just give you this picture, where on this picture it says the length of DE is 23 and the length of EF is 35, and it wants you to find DF, which is the length of the segment DF, so the length from here to here, how would you do it? You'd add them. You'd take the 23, you'd add the 35, and you would find that the length of DF is equal to 58. That's what the segment addition postulate says. It says that given this picture, I can take AB and add BC, and that will have to add up to the length of AC. It's a pretty straightforward postulate. The reason that I have to give it to you as a postulate is actually a couple things. One, we're going to be moving into proofs eventually, and you have to state your reasoning behind doing everything. But more importantly, people tend to get tripped up when it's not straight numbers or when it's not just like this. Okay, another one that is straight numbers. I want to find GH. G is here, H is here. I'm looking for this length. I know that from F to G is 21 and from F to H is 36. Is adding going to work this time? No, but subtracting will. Because according to the postulate, the adding would happen between FG and GH to be equal to FH. So the adding would have been the 21 plus the GH that we don't know is equal to that 36. That's what the postulate tells us. Now, it was mentioned, subtracting would work. Do you subtract to solve an equation that looks like this? Do you subtract to get GH alone when it's being added to 21? Yeah. Now, speaking of which, first off, I get 15. Let's chat about this equation real quick. One of the things that you are used to in an algebra class is you're used to every time you see a letter in an equation, it is a separate variable. But as we start learning new notations, sometimes you're going to have things be essentially a variable that are not a single letter in geometry. An example would be something that looks like this. GH represents the length of a segment. Remember, real quick, the name of that segment would be GH with the bar above it. Its length is without the bar above it. My point being, when you see FG, GH, FH, no bars above them, they are essentially, I did not click that. They are essentially variables. It's kind of like an X being right here for us to solve. Would the equation have looked a little more familiar had I written 21 plus X equals 36? Probably looked a little more familiar, but it is the same thing as doing this. I'm just not writing X, I'm writing the actual geometry notation. We do that in situations where there wasn't an X involved. If you really prefer, you could always have said, okay, if this is what I'm solving for, I'm going to call it X, and therefore 21 plus X equals 36. Or, on problems that are just straight numbers, could you have just subtracted? Yeah, if you recognize that, that's fine. Anyway, okay, we got two more examples. First one says find the value of X. Do you see a segment? Does it have 3 points on it? Anytime you see a picture like this, you want to look for what measurements you have. Do you have two partials of the entire segment? Do you have the full segment? When you know two partials and the full segment, that's when we do segment addition postulate. Now, you might be looking at me like, well, duh, Benson. The reason that I'm emphasizing this is we're going to get some other pictures that look a lot like this, but you approach differently as we go through the chapter. Okay, so because I know a part, and the whole, I could do segment addition postulate. What are the names of the parts? What's this thing's name? Names have letters. RS. Now I'd put the bar above it technically to name it, but right now I'm trying to write out the equation, and there's a reason why I'm writing out the equation with its names. That's the first part. Here's the second part. What's its name? ST. ST. Add the two parts together, we get the full thing all the way across. What's the thing all the way across's name? RT. I write this out because in the future we're going to have to write this out. If you skip writing this today, it's not the end of the world, but understand, we will get to a point where we have to write this. Okay. Traditionally, we would go directly to the variables though. RS, what's the length of RS? x minus 5. And I'd put that there instead. Plus, what's the length of ST? 9. Equal to, what's the length of RT? 2x minus 7. Okay, how do I solve an equation like that? Where do I start?
Did you combine -5 and 9?
You should combine your like terms, specifically the -5 and the 9.
So wouldn't you get 4?
You would get positive 4. X plus 4 equals 2x minus 7. How do I solve an equation that has x on both sides?
Minus x.
Move them together. If they're positive, you subtract. If they're negative, you add. I want to move a positive x, so I'm subtracting. 4 equals 2x minus x. 1x, or just x. Still got minus 7.
Subtract or
Add.
adding?
Am I adding the 4?
No, but the 7.
The 7. 11 is equal to x. Or I'd prefer x equals 11. Now, before you're done with the problem, double check that you actually answered what it wanted. Did we find the value of x? Sweet. Okay, final example. Do you notice it's the same 3 points in the same order? Which means it's RS plus ST equals RT again. What is the length of RS?
4 minus
X minus 4. What is the length of ST?
x minus 5.
What is the length of RT? 15. How do we solve? Where do we start? Add the like terms. What are the like terms?
-4 and 5.
-4, -5, is that the only one? The x and the x. Now when they're on the same side of the equal sign, do I do opposite operations? Like do I subtract x from both of these?
You just combine.
You just combine. It's a 1x and it says plus 1x. 2x. Now I'm saying this because it's one of the errors that I did see popping up on the quiz. -4, -5 is -9. I mean on the first quiz, by the way. From here, generally, y'all do fine. Add the 9, 2x equals 24. Divide by 2, x is 12. Did we answer what the question asked for? What did it tell me to find? RS. We solved for x. We needed to solve for x to find RS. If I want to find RS, I solve for x and then I ask myself, what's the measurement for RS? X minus 4, but do we know what x is now?
Yeah.
Since RS is equal to x minus 4, I can plug the 12 in. 12 minus 4 is 8. So make sure you're double checking what it's asking you to solve for.
Wait, what?
Because it asked for RS, I had to look at what it said RS was, and I plugged RX into it.